Okay, well, welcome everybody. This is the Global Ecosystem and Innovation track. This afternoon, we'll have a series of 10 different sessions. It'll be a mixture of both panel sessions and individual presentations. We will have a 15-minute break halfway through. And I am the track chair, so I'll introduce the various sessions. So this first panel is a panel session on competing quantum platforms. Talk about the innovation, strategy, supply chain implications. I will also be wearing a second hat as the moderator of this, so I'll be asking questions of the panelists about this particular topic. But let me start. Why don't we go down the line? If you just take like 30 seconds to introduce yourself and your company, and then we'll start with the questions.
I guess I have the mic, so I'll go ahead and start.
Yeah.
Hi, everyone. My name is Kristine Rezai. I'm the technical pre-sales engineer for North America for IQM Quantum Computers. I'm essentially the person with the physics PhD who's on the sales and commercial team. Who are we? What do we do at IQM? We are a Finnish full-stack superconducting qubit quantum computing company, so we do everything from the fabrication and design of the individual QPUs to designing the electronics, package that all, actually currently in a Bluefors dilution refrigerator. We work on the control software as well. We package all this up, ship it to our customers. One thing to note about us is that we've sold and delivered more full-stack quantum computers than any other quantum computing companies the last 5 years. Our first deployments in the US will be to Oak Ridge National Lab. So we're making inroads here as well as around the world.
All right, I'm Michael Eggleston. I'm from Nokia, so we're a leading telecommunications provider. We do all networks from fiber to radio access. I'm actually in Bell Labs, so I'm a research group leader. Really in Bell Labs, our mandate is to look kind of on a 10-year horizon and research the technologies that are going to be shaping the business that far out. So I lead really a physical device team, and we work on quantum technologies spanning compute, sensing, networking.
Hello, everyone. My name is Himadri Majumdar. I'm the co-founder and CEO of a company called SemiQon. We are from Finland. What SemiQon does, I will come back to during the moderation or the discussions. As for myself, I have a PhD in applied physics, but I have been doing innovation management for the last decade or so. As for operations side of things, I think it's good to understand a little bit about quantum computers, that when you see a quantum computer, you have the cryostat and you have the control electronics, and that's how it operates most of the time. And then the control electronics is outside. So when you think of us at SemiQon, think of that control electronics going inside the cryostat. And that's a teaser. I'll come back later. Thanks.
Okay, good afternoon, everyone. So my name is Sauli Sinisalo. I'm from a company called Bluefors, and I'm the vice president and general manager of our US operations here. And we're a company headquartered in Finland, Helsinki, and we have US headquarters in Brooklyn, New York. And like my colleagues already mentioned, so we do dilution refrigerators. We're the world leading manufacturer of those. And very often when you see quantum computer, you see golden chandelier dilution refrigerator, and that's very often our system. So we've actually produced 1,500 systems and counting around the world, and we produce more than 200 a year more. So that's our specialty.
Okay. Well, thanks for the introductions. So let me start up. But one of the debates that I always hear about is what technology is going to win. You know, we have like 8 different technologies, modalities in order to implement a quantum computer. And the question is it going to be a winner-take-all market, or will there be room for multiple players? And again, we're talking a little bit over the long term, not next year, the year after, but let's say in the 2030s. So, Kristine, let me start. I'll ask you for your take on that, and then we'll ask the others to chime in.
Yeah, it's an interesting question, and we're very much now in this time where it's very much a race. I mean, we heard some great keynotes and great presentations from a lot of different trapped ion companies. There's definitely kind of a lot of different players in the space. And at IQM, I mean, we are sold that superconducting qubits will ultimately win in this race. But of course, there's a lot of caveats to that. I think on one hand, you really have to win the technology race. So it is a question of who can actually get there, who can actually build and actually scale up their devices to have 1 million qubits. And I think that, once we've solved some of the technology challenges, there'll be some other more commercial challenges as well that I think there'll be a good question of, okay, then if we all get to this point, who will have, say, the cheapest system, the most power efficient system, the systems with the best uptime, systems with minimal downtime for calibration. There's a lot of different considerations that we'll get to kind of when we have some of these larger systems in play. So maybe in two parts, it still is unclear at this point. We do believe that superconducting qubits are kind of the way forward, but also put in the caveat that it may turn out that different modalities may also be better suited to different types of problems as well. Perhaps we're best suited to some types of problems, maybe sampling problems, perhaps, say, trapped ion or neutral atom quantum computers are also better suited for different types of problems. So maybe that's my almost non-answer, but we're currently sold on superconducting qubits, but I think there's room for other players, at least in the space.
Okay, how about Michael?
I like to take a kind of historical perspective on this. So the last time really the physical layer of our compute was kind of redone or invented for the first time was 80 years ago with the invention of the transistor. And you look back then, it was a germanium transistor. There was a huge race between germanium, gallium arsenide. It took over a decade before CMOS was invented. Right, so it took a long time before what is now the dominant technology was even demonstrated in a lab. It took another decade for that to actually reach commercial scale. Even you look today, though, CMOS isn't everywhere. Your cell phone, your power adapter to plug in your phone, those rely on non-CMOS technologies. And so when we look at quantum computing, quantum technologies, we really kind of see the same thing. There are dominant technologies now, but 10 years from now, I think it's really hard to say that that's going to be the case. And I think it's also really hard to say that there's going to be one dominant technology because there's just so many applications.
Thanks, Michael. You almost made my pitch. But no, I agree with both of you. And I think I would answer it from the SemiQon perspective. So as a company, like I said, we are doing control electronics in cryogenics, so cryo-electronics. And for us, we have a 3-horizon view on this. The first horizon is we don't know which modality is going to win. And what we do in that case is we know we build the electronics, which can be useful for multiple modalities. And that's what we want to help the community with. And then in the second horizon, like Michael said, in the semiconductor industry, transistors won. So if we are making the electronics with CMOS, we can also add the silicon spin qubit on top of that and build a quantum processor as the next thing. But I wouldn't perhaps dare to even compare them with the superconductings right now because the timing is not right in that sense. And the third horizon I will talk about later, but this is how it is playing out in the community, I think, that there are multiple modalities, they have all different advantages, but it will be multiple factors. So there has to be a figure of merit of commercialization as well, which will eventually define which modality becomes the winning horse. We are not there yet.
Well put actually. So there are of course multiple modalities, and which one will win? I think it really depends on also the full stack itself. So it's not just the qubit itself, what the different characteristics of that will be, but how do you actually build that into a commercial quantum computer, and what the application there will be. So of course. Building or developing technology that fits for many of the modalities. Really like that idea, and that's what Bluefors is doing as well. So we have almost all of the modalities at some level require cryogenics, and our specialties there. So that's we hope and see that many of the modalities will get commercialized.
Okay, so. Do you see at this point that there might be different modalities that are better for some applications than others? Or do you think maybe you don't see exactly what it is right now, but maybe you think that will happen in the future? And I'll start with Himadri.
Sure. Well, there are, I will reply it with a caveat of what Sauli said, that it's the whole system that matters. But in terms of qubit performances, I think there are those which have their inherent advantages in terms of gate speed, and some have inherent advantage of how you build the logical qubits. And so there are different ways of looking at it. And I think if you look at the various ecosystems in the world, when they are coming up with their national quantum agenda, they define something that they want to reach. And it's not always the same from those agendas as well. So, for example, I remember the one in UK where they are targeting 1 trillion gate operations, right? So that's a measure, but that's not necessarily the only measure to reach that. So.
Okay, anyone want to add to that?
I think I'll take a shot
go
at
ahead,
the
Kristine.
question. I guess the question is, for applications currently, are some modalities better suited to some of these applications?
And also
or algorithms
applications in the future.
In the future, yeah. I'll take a shot at actually answering
Okay.
the question for the present. So currently, I mean, if you just compare maybe superconducting to trapped ions, superconducting qubits are one of, if not the fastest modality on the market to date. And one of the real advantages of quantum computers is to be able to sample from distributions that are very hard to sample from classically. So for these types of sampling problems, superconducting qubits, I think, really are, I think, one of, if not the winner for these sampling type problems. However, if you want to execute, say, deeper, longer circuits with a lot more gates, I think that you're really limited in this case by the fidelity. So you may want to consider, say, other modalities such as like trapped ions, maybe neutral atoms as well, that have this higher fidelity for these applications where you're running a lot more gates. So it's kind of a matter of what type of problem do you want to solve. If you're trying to do something where you're trying to rapidly collect a lot of samples, then I think really superconducting qubits systems are really well tailored to those types of problems. But if you want to, say, execute very deep, very long circuits, then I think it's better to look at some other modalities that just have higher fidelity for the systems. In the future, I think things may change as all the platforms have better and better performance, but at least for the time being, that's at least kind of how I see things.
Okay.
Yeah, so I guess I'll add a take that's more than just computing, right? So if you want to communicate quantum information, you probably want to use a photon, right? That's probably the qubit you're going to go with. Not really any other qubit type can really communicate. If you want to go, if you have a sensing application, maybe a superconducting qubit's not the best. Maybe an NV diamond center might be the best, right? So I think it's incredibly, even now, very, very application specific. And in compute, I think most platforms now are just one type. But again, if we just look at what we do classically, imagine building a computer with just CMOS, right? No flash, no DRAM. It just really wouldn't work well. And so I think moving forward, that's really probably what we'll end up with, even in quantum computing.
Yeah, and to add to that, I think of course the other level is when you do cloud computing, and then you might have very different modalities available, and read it down it depends on what kind of problem you're actually solving, and then the cloud can help you find the best modality to go forward.
Okay. So. People talk about hybrid quantum computing, classical computing and quantum computing. And just recently, there's a startup, it's actually started by Chad Rigetti, if some of you know him, that's actually going to use, or they claim they're going to use, two different modalities, or two different types of quantum computers working together that might have different strengths and different weaknesses. Do any of you see any opportunities there, or do you think that's probably too complicated to actually make work?
I have a short answer to that. I think it's a good experiment to do.
Okay.
Yeah, I would agree. I mean, I think it's the right way to go, but it's hard to build single modality right now. So I think we're a little early for fully, heterogeneous architectures. So eventually, yeah, I think that's where we're going. But right now, I think it's a challenge, but definitely a good experiment to do.
Maybe I'll add something to that as well.
Yeah.
There exists some HPC centers that do actually have multiple modality backends as well. So this is something that you can also play around with. Like, for example, at LRZ, there's multiple quantum computing backends that a lot of users can access. So I'm not as familiar with the work in this domain as I think others are, but I think it's an interesting question to start to play around with, okay, these systems that have access to these different quantum computing modality backends, see what you can do if you connect quantum computer 1, say, to quantum computer 2.
Yeah, and to add to that, of course, the problem gets much more complex when you combine modalities, and there's still even the individual modalities. There's a lot to learn, but I very much agree what Himadri started. Though it's a good experiment, and we can learn a lot from it. And if you're able to convert that into some simple solution, actually going forward, often the simple systems win in the end.
Okay, so we have actually an unusual configuration of the panel. All 4 of those panelists are at least tied to companies in Finland. I don't know if that was on purpose or by accident. And then 3 out of the 4 panelists, though, live here in the United States. Only Himadri lives actually in Finland.
The real Finn.
But, you know, sometimes in technology what we see is that in different geographic areas, different technologies or different standards become more popular. And, you know, for example, in Europe they use 220 volts for their AC, and here in the US we use 110. Do you think that there might possibly be, you know, again, moving into the future, differences in terms of the most popular modality based upon the geographic area?
Yeah, it's an interesting question. I think, of course, while the technology is being developed and so forth, there's an instrumental effort coming from the academic industry, and some universities might or research labs might focus on different modalities, and of course, you're generating a lot of students that can potentially spin up of companies that then kind of situate in the vicinity, and I guess for our panel as well, so there's been a key research lab that has been kind of helping us along the way. But I think geographically, when you get to the point where you actually have the commercial products available and you realize that the market are actually global, then actually evens out the geographical distribution, I would say. Okay. So market evens that out.
So perhaps the world is a little bit more connected these days than it were 20 or 30 years ago or 100 years ago when electric power was first installed. Huh?
Yes.
Okay. Okay. So question for you, Sauli. If I'm a component supplier, you know, I want the widest available market with the least amount of customization for each individual customer. How do you handle the situation where I believe you sell your dilution refrigerators to superconducting suppliers as well as people who supply quantum dots? Do you have to customize anything at all, or is that an issue for you?
Yeah, I wouldn't say it's an issue. It's a challenge, and it's an opportunity.
Yeah.
I think in the development phase, very much so. So the core technology, like our helium circulation system, I think that's the same kind of principles that underlie in most of the products. Of course, yes, you want to customize things and work out engineering solutions that will actually create value for the customer. So you will definitely be customizing the products. In the end, of course, when the commercialization has gotten to a certain point, you can see if you can combine those, or you can tackle a couple of different needs with the similar product and with minor modifications. But yeah, customization is very, very key.
Okay, yeah, go ahead.
Yeah, I would actually take a point from Sauli's comment, and I think what matters at this stage for the quantum community is the ecosystem. And one of the reasons why you get this surprise number of companies coming out of Finland is because of the ecosystem. Bluefors is 1.5 kilometers away from us. We can go there and ask for customization. And these kind of advantages play in favor of not just building the supply chain, but also strengthening the ecosystem and the companies in that ecosystem. And now I gave the example of Finland, but there is no reason why it cannot be expanded further. And I think collaboration is a very essential part of how quantum community will grow. I'm not talking about any geographies here, but the community as itself has to collaborate to grow. And it also comes down to the smallest component that there is.
Yeah, and I just want to add to this, it kind of goes back to your previous question about if modalities will be kind of geographic. And I would say I really hope not, because that means kind of open science falls apart and open markets kind of fall apart. And what we kind of want to avoid doing is solving the same problem over and over, because there's a lot of problems to solve in quantum. So I don't think we need to come up with more challenges. So I think sharing and building that ecosystem is key.
I think I'm all good.
Okay. Let me think about the perspective of an end user. So I'm an end user. I'm trying to develop a program. And I listen to these pitches from Microsoft and AWS, Amazon. They say you can write one program, and just by one line of code change, you can switch back and forth between one computer to another in different modalities. How well do you guys think that works? Switching back and forth, from one thing, or do you really, when you develop a program, do you really want to start almost from the beginning, targeting a specific modality to optimize your program for that modality?
So I'll give a quick answer, because I'm a hardware guy. But I think it's challenging. And even like if you write something for a CPU and you want to put it on a GPU or a TPU, it's really hard to do the translation. You can do it, but can you do it well? And so there's just a lot of room for optimization when you're actually moving hardware platforms.
Also take a shot. Yeah, it's a matter of also how much performance you want out of your code. I think it is possible to almost copy paste if you don't really care about if the end result is good or not. But I think if you want to get the best performance out of whatever hardware you are running on, then I think it's worth knowing and understanding the hardware, the connectivity of the hardware, which qubits are good, which qubits are not so good on your chip or in your device. I think there's some amount of work that you need to do, maybe not so much on developing a new algorithm, but on kind of the compilation, transpilation, kind of some of the later stages of the process.
I'll have a general comment on that, and it's related to, I would look at it as the responsibility of companies like AWS or whoever is providing that stack, because they are the front line of quantum, and people who want to try quantum come to them for seeking an answer. And if they do not find the right modalities to solve the right problem, then there is a room for disappointment as well. So they have both an opportunity to deliver to the end users the right solutions, but they also have the responsibility of choosing the right hardware that they should be coding that specific problem in.
I don't have much to add. I think great answers already, but I think very much so. So if we can, or for example, in this case, AWS or Microsoft can kind of help to migrate your code between the different modalities. It's a great platform to test out and kind of learn about the specific characteristics or performance metrics that matter in different modalities. But I think in the end as well, like Kristine said, that if you want the best performance out from your code and your system, you need to know the hardware and the software and the middleware and your application.
Okay. So we only have 5 minutes left, but I want to leave some time for the questions from the audience. Does anyone in the audience have a question? Yeah, go ahead.
Is the community coming together on standards of it?
Standards, a very good question.
That was my point in the collaboration aspect. So, sorry. So when you collaborate, you come together to build standards as well. And it is very likely it's going to be a geographical war again. So let's try to avoid that.
Yeah, I think, I mean, standards are difficult. Nokia loves standards. And we're starting to look at standardization, more advanced technologies, things that have been out there longer, like QKD, you know, you're getting standardization. But from what I'm seeing, a lot of it is just, it's too early to really have these formal standards.
Yeah, I agree, and I agree that standards are very important in kind of mature technology. I think you need to work together with the customers, work together with the ecosystems to find what works and what not works, and what's the best solution for whether it's interconnection or whatnot. But yeah, in the end, the best solutions typically are strong in when the standards are being created. So that's the point.
Okay. Anything else from the audience? Yeah, go ahead, back there.
Yes, so last year I heard that in IQM, they have the people are working from the people working there at IQM are from maybe 40 nations.
Yeah, I think it's more than 50 at this point. It's interesting and it's challenging. Actually, maybe was that the question, or what? Maybe I'll let you finish the question.
Okay, I would like to know even though these companies are located in very northern Europe, but people from many other countries are coming together and collaborate each other. So I would like to know how many nationalities do you have in each company?
Oh, are we over 50 or over 60 nationalities? Wow. It's varies. We have, so our primary base of operations is just outside of Helsinki. We have a secondary office in Munich, and then we have a bunch of satellite offices. So yeah, I'm here in the US, but we also have folks in APAC, kind of throughout the world, plus people from around the world also just come to Finland as well to do quantum, and it's not just at our company, but also in these other great companies. So it's very interesting.
Yeah, so I think Nokia focuses on countries that need networks. So that's most of them, I think, if not all. And from Bell Labs, I mean, Bell Labs alone has 14 sites scattered around a dozen different countries. And even like our headquarters is in New Jersey. I think 10% of the employees are American nationals. The rest come from all over the world.
I have to answer that. It's one of my favorite pitch part, which I couldn't come to. We are a 25 people company, and we are 8 nationalities. And the point that we want to make, and we try to make, it's driven by experts. We don't really care where the experts come from. We celebrate the expertise that they bring. And that's what makes, I would say, any company a great company.
Yeah, along the same lines with Bluefors as well. So we are globally about 700, I think 650, 700 people. And at some point it was 52, the different nationalities in the company. And it's been since the beginning. So founders are Dutch and building a company in Finland and kind of getting the top talent from the academia, for example. It comes with different nationalities, and that's a very strong advantage.
So maybe the kind of diversity might contribute a lot to the stability and the strength of the company.
Yes, exactly.
Okay, so we've run out of time. Let's give a hand for the panelists. Great session.